A sequence is a list of numbers. Just a list. That's all it is. So 1, 2, 3, 4, 5, there's a sequence. 2, 4, 6, 8, 10, there's another one. Just a list. We have a couple different ways of expressing a sequence. If I write AN, that means the nth number in the sequence. That's all, or we call it the nth term in the sequence. So then we have to talk about n. If AN is the number that's in the sequence, n is just a counter. It tells me where I am in the sequence. So if I say A1, that means the first term of the sequence. A2 is the number in the second place in the sequence. A62 is the number in the 62nd place down the line of the sequence. So n just counts. Where are we in the sequence? We have a couple different ways of expressing sequences. One of them is, if I know one term in the sequence, I can use that to find the next term. And that's the idea of a recursive definition. I'm going to use the current term to get the next term. An example of that looks like this. If I have AN equals, well, let's see. If I'm on term AN, I'm going to use the one that came before that. So that's the one before it was the n minus first term. AN minus 1, and I'm going to do something to that to get the next term. Well, here's what I'm going to do in this particular one. I'm going to take the last term, I'm going to multiply it by 2, and then I'm going to add 3. So we can build up a sequence using a recursive definition like this. One other thing I have to use a recursive definition of a sequence is I have to know where I started. I have to know what the first term is. Otherwise, I can't find the second term without the first term, so we have to say out loud, here's the first term. I'm going to have A1, B7. So I'm going to find the first few terms of this sequence using this recursive definition. Starting with A1, but I already know what A1 is. A1 is 7, because it says so right the line above. Well, that's nice. I didn't have to do anything to get that. Let's find A2, the second number of the sequence. Well, not like that. Try again. Here's A2. So A2 says I'm going to take 2 times the term that came before. The term that came before was 7. A1 was 7. I'm going to multiply it by 2 and add 3. 2 times 7 plus 3, that sounds like 17 to me. So there's the second term of my sequence. For the third term, I'm going to take the second term and apply that same thing to it. So for A3, I'm going to take 2 times the one that came before. Well, that's the one I just found, which was 17. So I'll take 17, multiply it by 2, and add 3. Let's see, 34 plus 3, that sounds like 37. Let's do one more, A4. So to find A4, I'm going to use the term that came before, which is A3, which is 37, which I just found. So according to the recursive definition, I'm going to do 2 times the number I just found, the number that came before, 37, and add 3 to it. So 2 times 37 is 74 plus 3 is 77. And there are the first few terms of my sequence. If I want to write the sequence, A1 was 7, A2 was 17, A3 was 37, A4 was 77, and so on. This is great if all you want to do is go down the sequence. If I want to jump in the middle, this is not so good. If I want to know what's the 43rd term in this sequence, I have to find the first 42 terms in order to get there. Really don't want to do that. For that reason, we have a different way, another way of finding terms of a sequence. If I want to find any term of a sequence or a general term, the idea with a general term is I can jump in anywhere in the sequence that I want. And the definition for a general term is going to involve only n, only knowing where I am in the sequence, what term of the sequence I want. Oops, making up words again. Uses only n, the number of the term. An example of that, of a sequence that works this way, this time, oh, I did want that to say n, an, after all that, there we go. Okay, back where I started, an equals, this sequence is going to go n squared minus 2n minus 1. Here, I don't have to say out loud what the first term is. I can find it because this sequence, this definition depends only on n, where am I in the sequence. So let's start off with the first term. I'm going to find a1. For this sequence, this is exactly like a function. In fact, it really is a function. a1, I replaced n with 1, so I'm going to replace all the n's with 1. a1 is, instead of n, it's 1 squared minus 2 times 1 minus 1. And we'll just order of operations and crunch the numbers there. Let's see, 1 minus 2 minus 1 sounds like negative 2. For a2, I'm going to do the same thing, except for this is the second term, so I'm going to replace all my n's with 2's. So for a2, that's 2 squared minus 2 times 2 minus 1. Let's see, 4 minus 4, we're back to 0, minus 1 is negative 1. So there's the second term of the sequence. The third term, a3, try again, a3. That really just wants to be a 3. I can't just call it 3 because then I'm going to have 3 equals something and it's probably not going to be equal to 3 on the other side. And we don't want to say something is equal when it isn't. There we go. Okay, a3, the third term in this sequence, I'm going to get by replacing the n's with 3's, exactly like you would in a function. So I'm going to have 3 squared minus 2 times 3 minus 1, which is 9 minus 6, I'm down to 3, minus 1 is 2. So there's the first 3 terms of my sequence, negative 2, negative 1, 2. Here's the real beauty of the general term definition of a sequence, though. If I want a30, the 30th term of this sequence, I don't have to go through all 29 of the terms that came before it to get there, like I would have with a recursive sequence. I can cut to the chase here. a30, I'm going to replace all the n's with 30's. It's 30 squared minus 2 times 30 minus 1. And we can do that. Let's see, 900 minus 60 is 840. Minus 1 is 839, not 1839. We can jump right in the middle anywhere we want and find a specific term of the sequence.